Probability density and cumulative distribution functions. It is important to note that since the variable is continuous, there are an infinite number of individual values that could be taken. I've spoken about this in an earlier video. Thus, as mentioned earlier, the probability of any particular value, that's any individual value, being taken is 0. Hence, if you are asked for the probability that x equals 3 for a continuous random variable x, you will always write the probability that x is 3 is 0. We can, however, talk about the probability that x takes a value in a given range, as we did in example 1 when we looked at the relative frequency histogram. This gives us the idea of probability density, i.e. the likelihood that x lies between two values. As you can appreciate, over the entire domain, the probability it lies between two particular values might change quite a bit, even if those two values are the same distance apart. In other words, as we saw with the histogram, the bars of the histogram varied in height. Typically, the graph of a PDF, probability density function, is a curve, and the total area under that curve must be 1. This is one of our key features. Remember, the probability of a certainty is 1, and the probability scale goes from 0 to 1. Here we have an example of a probability density function which is non-zero between a and b, and we would consider it to be 0 everywhere else. We could state the PDF as f of x is some function p of x between a and b, and it really doesn't matter whether these are less thans or less than or equal to's, because the probability of taking a particular value is 0. And then we would also say that it's 0 otherwise, that's outside of the range a to b. Or f of x is equal to p of x for the interval a, b. And once again, when stating an interval, here I've used these sorts of brackets with the square brackets, and that means a and b are included. So that's the same as having less than or equal to's here and here. Doesn't matter if they're round brackets, indicating that a and b are not included, because the probability of it taking the value a is 0, and likewise with b. So, I think we need a quick note on intervals here. I've just spoken about it a little bit, but you may not have met this before. So let's be clear. If we have square brackets, AB means that x is greater than or equal to a, but less than or equal to b. So x is between a and b, including a and b. If we've got round brackets, it means this. So x is between a and b, strictly between a and b. It can't be a, it can't be b. If you have a square bracket at one end, that end is a less than or equal to, and the other end just a less than. And the same thing if we have the round bracket this end and a square bracket that end. If we have 0 to infinity, that means x is greater than or equal to 0. The infinity must always have a round bracket, because you can't actually be equal to infinity. Whenever infinity is used, the bracket must be round, as just mentioned. Infinity is not a number. With continuous distributions, it does not matter whether we use the square brackets or the round brackets, as the probability that the variable actually takes the values a or b is 0. We've mentioned this a couple of times, but it's such an important point. Just be consistent with any question that you've been asked. If we wanted the probability that the variable was to take a value between, say, c and d, then what we would want is this area here. If we know p of x, we can calculate this using an integral. So that would be the integral from c to d of p P of x. Any probability density function must satisfy the following conditions. P of x must be greater than or equal to 0 for x in the interval AB. Think about this. You cannot have a negative probability. The probability scale goes from 0 to 1. So you can't have a PDF where the curve goes below the x-axis. The integral from a to b of P of x must be 1. We know that 1 is the probability of a certainty. The probability scale goes from 0 to 1, so it can't be more than 1. The cumulative distribution function, CDF, tells us the total probability up to a given value. So for example, here, we're starting at the beginning at A and going up to C. This area would be the integral from A to C of P of x dx, and would represent the probability that x takes a value between A and C. In general, notice this is capital F because this is the cumulative distribution function. The area is 0 if x is less than A, and that's quite clear on here. We know the PDF is 0 back here before we get to A, so there's no area above the curve. Then in between, it's the integral from A to x of P of x dx. So for any particular value, like the C, so let's say this one is a general one, x, we'll add this area on, then we want this total area. So it's the integral from A to x of P of x dx, and then 1 from then on, because once we reach the total probability of 1 when we get to B, we can't add any more area on. But the cumulative function always stays as 1. Just think about this. Suppose this value here, b, was 2. Then the probability that x is less than or equal to 2 is equal to 1. But that's also true of x being less than or equal to 3. And that's why this is 1 forever.